Okay, the first one, this is just the list on the left side of the data values, and on the right, frequency means how many times it occurred in the data set. So think about this like maybe ages of some student group, okay? And then this is how many of those students were each age. That's what a frequency table means. So when it says what is the maximum data value, what would you say it is? Okay, so let me start over. This is the data, like the age, if we're picking an example, this is the ages, and this is how many people. Okay? So the maximum data value is 14. Would be the oldest kid, right, in the list, in the set of data. Whereas the 6 or the 11 is the maximum what? Yeah, that's the most kids. So there's the most 11-year-olds, because there's 11 11-year-olds. There's only 6 14-year-olds, but they are the maximum value. Okay, so this is data, and this is how many times it occurs. Good on that? I feel like that should be a gimme if they put one on there like that. So just read it carefully. Data value, maximum data value. Oh, that's the data value column. All right, other one. I doubt anybody has studied this, but you can see that it's potentially on SAT. So have you ever heard of radians before? No. Okay. If you take pre-calc, we don't measure after this class. Actually, this class should get to it. We just never have time. But we don't measure angles in degrees anymore. We measure them in radians. Okay. So what I just told you was radians are a degree measure, or a unit of measure of angle size in a circle. Okay, quick reminder, some circle. How many degrees are there all the way around?
260.
Okay. A radian does the same thing in terms of measuring angles in a circle. And you could, I suppose, do it in a triangle. We don't usually do it that way. But there's only 2 pi radians in a circle. So which one is bigger, a degree or a radian? Like, what is the approximate value of 2 pi? Just a little over 6, right? So there's only 6 radians to cover the whole circle versus 360 degrees. So which one is bigger? A radian is way bigger, like almost 60 times bigger, right? In other words, like a degree might be about the width of that mark, probably a little less actually. Whereas a radian would be like 60 degrees of the whole thing. Like it would take up a huge chunk of that arc instead of just a little teeny piece. Okay, anyway, this is a conversion factor between degrees and radians. I'm going to do the work up there. So 360 degrees for 2 pi radians. Have you ever seen rad on your calculator?
Yeah.
That's what it's either deg for degrees or rad for radians. Like I said, after, even in Algebra 2, but after for sure, you don't use degrees as much. Okay, so let's read the problem now that we have some background. The angle R is in 2 pi over 3 radians. That's how we say that, 2 pi over 3. The measure of angle T is 5 pi over 12 radians greater than R. So T is 2 pi over 3 plus 5 pi over 12. Okay. It's wanting us to pick from a degree measure. Now that you know a little bit about this, let's see if you can do it. There's not a lot of calculating involved. Tell me, we always start on the positive x-axis, so this is 0 degrees. So what would this be over here? And we go this way, counterclockwise. So that's 180 degrees, okay? So now I want you to think in terms of radians. It's still 0 radians, But now by the time we get back around, instead of 360 degrees, it's 2 pi radians. So how many radians would we be here halfway across? 1 pi, right? If it's 2 pi to get all the way around, it must be 1 pi to get halfway. Okay, everybody with me so far? Alright, so again, we don't have to do a huge calculation. We just really need to simplify this, and it will tell us where to look in our answers. So how do we add those two fractions? It's just regular fraction adding with a pi stuck in there. Okay, so same denominator, which will be 12. So how do we make this 12ths? This is good for our current unit. We'll be doing a lot with common denominators. How do you make thirds 12ths? What? Holy cow, you guys, do you not know how to add fractions? Like if it was just that, seriously, quit doing it. What would you do? You're kind of shocking me right now, for real. Nobody in here knows how to add those two fractions. Okay. You can see to me why SAT is stupid. Because we're sending kids out into the world that can't measure their recipes, but we're trying to teach them radians. It makes no sense, right? How do we get this third to be a 12? This 3. Okay. Can I just multiply the denominator? No. So you have to do the same on the top. This now becomes what? 8 thirds. And then 5 twelfths. 8 twelfths, excuse me, not thirds. And then we have these pi's here. In this problem, we have the pi sitting there too. Okay, so how do you add fractions? So this is what? 13 24ths? Okay, good. 13 pi over 12. Roughly, how close, like where is this on that circle, roughly? 13 12ths pi. Yeah, it's just about half, right? Is it just before or just after half? Why just after? What would it be to get just halfway? What would this number have to be? 12, because 12 over 12 is 1. That would be pi. So that would be right there. Okay? So 13 12ths pi is just after. Out of this list, which one is just after halfway around? $1.95. Okay, so really this is a fraction addition problem, as long as you know that there's 2 pi radians in a circle. Whew, all right, grab your stuff from here. Okay, first line, again, we're not perfectly graphing these, we're just sketching the graphs. Let me know, and I can probably get the next line up there, actually. I'm hoping VA and HA were clear that that's vertical asymptote, horizontal asymptote. Okay, middle and bottom row. the bottom, you had to write equations.
Hold on. I don't know my notes.
You had to write equations that give the asymptotes that were shown. In other words, find H and K and plug them in. That's really, you don't even have to find them, just plug them in.
Yeah, okay. So, if that.
How'd it go? Okay. Good. Blake?
Then it's gonna
Okay.
be.
Who else?
Is it this one?
Good. Good. How about you guys? Did you get to it? No. How about you? Trinity? Good. All right.
So I have a question.
Yeah.
What if it is one? No,
What if what?
if A is less than or equal to, or less than or more than one, like what happens if it is one?
Oh. Do we have any like that? 13. This is what you're asking about, right? Okay. Basically what that means is it's just the normal shape, just moved. Okay? So we're not, you know how we said if A is greater than 1, it pulls away from that origin, from our the intersection of our two asymptotes? And I'll clarify that in a second, but, and then if it's less than 1, it's closer. But if it's 1, it's just the normal distance, meaning over 1, that very corner point is over 1, up 1 from wherever our new origin is.
Oh.
Okay. So guys, in terms of clarifying what I mean by pulling away. So on this was, take a look at what we had. The pink one is just parent 1 over x. The purple one is 1/2. A is 1/2. So what I meant when I said it pulls farther away or closer is diagonally out from the origin. Diagonally. So if I had A, like if A was 4 or whatever, some number bigger than 1, it would curve through where this region is wider. Okay? It's further away from that corner. But it's still going to approach out to the right and up. It's still going to approach our asymptotes eventually. Okay? So, I don't know if that's more clear. And then in this case, A was 1/2. So instead of coming like this far away, it was just a little teeny bit far away because it's at that corner where it turns to go the other direction. It sucks in more towards the origin is what I meant by either further or closer. Does that help? Okay, so ask me a question. Like what's not clear?
Like I'm so confused on the full way.
Okay. Maybe if we graph in Desmos, that would help maybe. Because then you can see them compared on the same exact graph. Okay. So here's the parent function. Let me zoom in so you have a scale. Do you see how it approaches the x and y axis like normal? If we change the numerator to, let's do 5, what do we expect to happen? Okay, do you see how the black line is farther? Like here, it's here going out to the right and up towards the y-axis. It's still coming down the same way. Like eventually it will be right on top of that purple line. But this part pulled away, diagonally pulled away from the center. Does everybody see what I'm saying now? Do you? If we did 10, it would be even further. I'll put that on here, okay? So I'll leave the 5. If we make, the bigger that A gets, the farther it goes out away from the center, okay? And then if we make A smaller, So let's do like 0.5. A half. That's what we graphed on that example the other day. See how it pulled in closer than the purple one? The purple one is our parent function. Okay, if we did like 0.1, it's like sucked right in there next to the origin, right? Okay, so a smaller than 1, it's getting closer. And I'm talking about the corner. Notice that all of these lines eventually will be right on top of each other as we go out to infinity in either direction. Okay, bigger A, it pulls farther away. And all of this is true if I went and added something to the denominator. So if we did like +2 for all these denominators, it doesn't change their shape, just where they are. Okay? In fact, let's add something at the end so it's even more obvious. Let's do like +3. Okay. So do you see our new origin is right there? Okay? Everything is still either closer or farther away, same as it was. It's just all referencing off of that point now instead. Instead of the actual origin, it's referencing off our new one, where our asymptotes are. Does that help?
Yeah.
Okay. Yeah, definitely. I'll post a screenshot of this if you want to re-reference it later on. Any other questions on that? Okay. The interesting thing about this unit, so this, we were talking about the reciprocal function, and now we're going to switch over and start calling it rational functions because we're going to complicate the functions a fair bit. But the interesting thing about this unit is that it actually gets easier in some ways to understand how the graphs look. In some ways, not all of them. So let me show you this one. What is different about this than what we did on your homework? Yeah, we have, well, sorry, don't worry about the directions, but we're not going to actually do that. But do you see how there's an x in the numerator now? So how does that change the appearance? Before it was just a number, and that number was telling us kind of how far or close to the origin the graph came. Well, what does that do? So we need a way to figure out our asymptotes when we have more complicated numerators and denominators. Here's our goal. Let me show you what, like we want to be able to do one like that. Okay? And so we need a procedure for finding where does it approach vertically and horizontally. Everybody clear on what we need to do? Okay? Our graphing will only ever consist of sketching in this unit. So you can use graph paper and I will give you grids, in fact, but it's not like you're going to go graph each individual point. Okay? So if you know that you can find your horizontal asymptote maybe there and vertical asymptote there, then as long as you know to come in here and sketch a graph like that, or perhaps it's like this version, you're okay. Okay? So I'm not going to grade on did you put it here versus it should have been here. Does that kind of help? Because a lot of the work of the unit is finding the asymptotes, and if there are any holes in the graph where a point doesn't exist, you'll need to show that. And we have procedures for all this. It's pretty straightforward actually, okay? As long as you can factor. So, I'm trying to put your mind at ease. I'm hoping it's working. Does it feel like it is? Okay. In fact, let's start with this one, because the question in the red says, what makes the denominator 0? So why would that be a question of importance? Think back to the work you were doing in the homework and on Wednesday. What happened as the denominator got close to 0? What was it?
It got closer to the origin.
No. Technically it didn't. Pull out one of your graphs from yesterday, from Wednesday. I'll put it on here too, like this one. What happened as the x values got closer and closer to 0? Do you see how stuff starts blowing up, like turns a sharp corner and goes either super high or super low, right? To infinity, in fact. Why was that? You're dividing by a smaller and smaller and smaller number. And so we've said, like, divide by a cookie by the number of atoms in it. And it's billions and trillions, right? So if I say, hey, a cookie divided by this teeny, teeny, teeny little atom, that's a billion or trillion pieces. Make sense? Or you, how many cells are in you? Okay? Trillions of cells. If I divide it by negative, it's negative trillions. It's the same thing. Okay? So as we get closer to a 0 denominator, because we're dividing by smaller and smaller pieces, they start to head in opposite directions and it blows up, in most cases. So that's our asymptote, isn't it? That's where that happens. Okay? I see some confused faces. I feel like sometimes just writing it down, at least it gives you something to look at. Then we'll talk about how to find this. But it's pretty critical to understand that concept. Like Henry was able to say, oh, we're dividing by smaller and smaller pieces. That shoots the value up. I need you to get there. Everybody in the room needs to understand that. Otherwise, this will always go over your head. Okay? So that's what we're about to write. I'm writing this part out on the side so it hopefully catches your eye. And it really comes down to an understanding of what division means, okay? And if, like, that probably was developed over your elementary and middle school years. So if you need to come talk to me about that, let's make sure this is clear. Okay? So dividing by a smaller and smaller number, think about pieces. Actually, I'll write that at the end. Makes the result huge. I'm going to say, this sounds weird, but huger and huger. And I think it's because we usually divide by bigger numbers. You've all had pizza, maybe at a party. There's one pizza. You have 10 people. How much of the pizza do you get? A tenth, right? It's a smaller piece. But if I start saying, how many crumbs are in that pizza? What are you going to say? Yeah, like what? Like 1,000,000 crumbs, right? Do you see how if we, like we're picking to divide in big chunks, but if we divide by little teeny chunks, now our number shoots up. How many crumbs are in a pizza? How many molecules are in the pizza? Well, now each crumb has thousands of molecules, so now the number's even bigger, right? And if we start looking microscopic, like how many atoms of carbon are in the pizza? Like trillions, right? As we look at littler and littler pieces of that pizza. That's this. That's why as we go to 0 in the denominator, that it's blowing up. Okay? And I guess we could say just that kind of mind picture. Actually, I'm not even going to use the word division. Think of it like this. Think of how many crumbs are in a pizza. And just say it's huge, right? But can we ever divide that pizza by nothing? You know, if I say, oh, atoms, oh, now I'm saying maybe electrons, like just get teenier and teenier, but can I ever just say divide by nothing? No, because that doesn't make sense. Now I'm not dividing anymore. So, smaller and smaller number, but never 0. Okay, this is a really, really big deal. So please maybe put this, somehow make this stand out. So our vertical asymptote, that number that the graph approaches but never touches because it's happening to make the denominator close to 0, this whole process, that's our vertical asymptote. That's what creates our vertical asymptote. So our next note is going to reference off of this one. Actually, let's just write vertical asymptote here so you can see it in your notes nice. Okay, so I'm writing this process, this one we just wrote about, dividing by smaller and smaller pieces. That's where the vertical asymptote is found. Where does that happen? It happens at, let's be a little more mathematical now. At the x value, where the denominator is 0. Okay? Just, we can stick it in that one. Yeah, thanks. So, in order to find vertical asymptotes, set the denominator equal to 0. That is literally what we do, and then we solve for x. How many times have we done that before? Yeah. Set something equal to 0. That was almost all of fall and the first part of this semester. Was setting things equal to 0. So you've done this a lot. It's just now taking that skill and putting it into a slightly new concept. Okay, so looking at this, how are we going to find where the denominator is 0? How are we going to find the equations of the vertical asymptotes, or perhaps there's just one? How? What did you just write? Huh? Set what equal to 0? The denominator, okay? That's just this piece. Okay? In other words, to figure out where this function is undefined, meaning it has a vertical asymptote, we just set that part equal to 0. How many times have you solved an equation like that now? A whole bunch, right? In fact, you can probably solve it in your head right now. Anybody there? Yeah, some of you? What are the two zeros? -4 and -3, right? So those make this 0. If we're on those points, this has a vertical asymptote. That function won't exist there. Okay? if we set the numerator equal to 0, what are we finding? Is that the same thing? Like if this was 0 over x squared plus 7x plus 12, what did we find in that case? What is the value of 0 over something? It's nothing. So we found the what? It has a name. We've done it 8,000 times. No. Where is a function equal to 0? The x-intercepts, right? The x-intercepts. So that's a thing. It's not as big of a deal as finding the vertical asymptotes. Okay, so let's take this function over to your examples, and I don't want the question mark. All right, so this we already wrote. It's basically a short note over here on the steps wise. Are you guys good with vertical asymptotes as VA? Yeah. Okay. What do? Set what? The denominator equal to 0 and solve for x. Now you could have any kind of different function in the denominator. Like that could be a cubic function. What if it was a 4th degree? And we're back to the last unit doing rational root theorem to find our asymptotes. That'd be a lot of work, right? Now, that's not going to happen, but just know that it's fine if it did. It's not something we couldn't do. So x squared plus 7x plus 12 equals 0. Factor, if you need to write out your star, please do, but the factors are x plus 3 and x plus 4. So what are the two zeros? Okay. Zeros are x equals 3, not 3, negative 3, and negative 4. Okay. Over here, I want you to put a pretty important little note. These are vertical lines. Write the vertical asymptotes as vertical line equations, which means they have to say x equals. The good thing is when you're solving, if you say x equals like we did, it's already in the form of a line. So those are our two asymptotes, x equals negative 3 and x equals negative 4. I'm going to write it again just with that new title, but it's no different. We haven't seen one that has two. What do you think the graph would look like if it has two lines that it can't touch vertically? You don't need to sketch this, but think about where these are. Negative 3 and negative 4. We know that our graphs have this kind of shape, right? So how is that going to play into this kind of a situation? Any thoughts?
Wouldn't it just separate the distance?
Yeah. Something like that. Okay? Those butterfly wings, that's what they look like to me, are just separated by that gap in between. And usually what that means is in between there's either an upward parabola or a downward parabola in between there, and sometimes it's like a cubic function in between. Okay, we're not there yet. I don't want you to worry about that. You'll be able to do that soon. But for now, butterfly wings in their usual spot. Okay? How do you feel about that? Okay, one thing we don't know is the horizontal asymptote. I drew it like it was 0 at the x-axis, because it is, but we don't know how to find that just yet. Any questions on finding a vertical asymptote? Okay, so it's really just finding zeros. Is today a 25 day?